Properties of logarithms, examples. Let's remind ourselves quickly of the properties of logarithms that we talked about in the last video. So the log of 1, any base, is 0. Then when we have the log of two things multiplied, I'll call it x times y in this video. We can add the logarithms. So if you have not watched the video where I introduce the properties of logarithms, I recommend that you go back and watch it now if you want to understand it a little bit better. The next property of logarithms, we have the log base b of two things divided. We will subtract our logarithms. And then finally, when we have a logarithm with something raised to a power, we can bring that power down in front and multiply. So you might want to have these properties written down by the side so that you can see them as we scroll through. But we're going to use these properties first to expand some logarithms as far as we can, and then afterwards to compress logarithms. Let's take a look at our first example. Log base 2 of x squared times y cubed. I'm going to use the properties one at a time. When you get comfortable, feel free to do all properties at once. But I will start with the multiplication / addition property. So I have log base 2 of x squared times y cubed, meaning I can rewrite these as the log base 2 of x squared plus the log base 2 of y cubed. That is, multiplication inside my logarithm becomes the addition of two logarithms. I'm now going to use the property where I have something raised to a power. So here I have log base 2 of x squared. That 2 is my power. And I can bring that power down in front and multiply, giving me 2 log base 2 of x. Similarly, with log base 2 of y cubed, the 3 is my power. So I can bring that power down in front and multiply, giving me 3 times log base 2 of y. And I have successfully expanded my logarithm as far as I can. Let's take a look at another example. Let's do the log of 3 root x over y. Now, you may recall, or you might not, that I have the log of something, called log of x, without a number here. For us, we know or assume that is going to be the log base 10 of x. And when we see the natural log of x, that is the log base e of x, where e is a number about 2.718, but it goes on forever and never repeats. We call it an irrational number. Back to our problem. Notice I have 3 things here. I have a multiplication in the top, so I can do log base 3 plus log base, not log base 3, but log 3 plus log root x. And then I have y in the denominator. I'm dividing there, so I can do minus log of y. So all of these are log base 10, first of 3, then of root x, and then of y. I can go a little bit further with this middle piece if I remember that the square root of x is x to the 1/2 power, meaning I can rewrite this as log of 3 plus, and then since I have x to the 1/2 in here, I can bring that 1/2 out front, give me 1/2 log of x minus log of y. and I have successfully expanded my logarithm. Let's do one more, and I'll give you a natural log, which of course, as I just said, is log base e. Let's do the natural log of x squared times the cube root of 1 minus x all over y to the fourth times w to the fifth. So I have two things in the numerator being multiplied and two things in the denominator being divided in the entire scheme of this problem. Let me rewrite this one first. I have the natural log of x squared, and then I have 1 minus x cube rooted, or 1 minus x to the 1/3 power. So I'll do that fix first, just to help us see a little bit better how to rewrite it. And then I'm going to expand this using all the properties at once. That is in one step. So I have natural log of x squared becomes 2 natural log of x. And then I would do plus natural log of 1 minus x to the 1/3. So 1/3 natural log of 1 minus x. And then minus, and I could do minus and some parentheses because it's being multiplied on the bottom, but I like to think of it this way. If I have something in the numerator, I know it's going to be added. And if I have something in the denominator, it's going to be subtracted. So the back part will be minus 4 natural log of y minus 5 natural log of w. As stated, I do want to see it here. I could have subtracted the entire denominator instead and say, well, it's multiply. Why isn't it not addition? It is, but it's minus the entire thing, right? So if I had decided to do it this way instead, which is mathematically correct, I would have subtracted the entire denominator, and then I could distribute, which would give me exactly what I started with up front. So let's work it the other way. What if we had the following? 3 log base 3 of x plus 2/3 log base 3 of y minus 5 log base 3 of z. Can we put this together into one logarithm? Since we have the same base for all of these, log base 3, we certainly can. And I'm going to do this one in steps. So I'm going to use the property of kind of the powers, but backwards. So where the property, or that the 3 was out front and being multiplied, I could move it up top to become my exponent, which is what I did. Log base 3 of x cubed. Similarly, this coefficient out front, the 2/3, can be put back inside as the power of my y, giving me log base 3 of y to the 2/3. And the same thing back here with my z. So minus log base 3 of z to the 5th. Now I have all the same base still, so I can make 1 log, say log base 3 of what? Well, addition becomes multiplication inside the argument of the logarithm. So I have x cubed times y to the 2/3. And then subtraction becomes division inside the logarithm, giving me over z to the 5th. How about this one? What if we do the log of x minus 4 log of y minus 2 log of z. Can we make this into one logarithm? Well, do we have the same base? Recall that when no base is indicated, we just have log, it's log base 10. So we do have the same base, and we can put this together in the following way. The first one is positive, so that's going to be in my numerator. The next two pieces are negative, so they will be in the denominator. The first one as y to the fourth, and the second one as z squared. And there we go. We've compressed our logarithm statement into one logarithm. Let's take a look at one final example here. Let's do the log base 2 of 4 minus the log base 2 of 32 plus the log base 2 of 2 cubed. Let's put this together into one logarithm and simplify it. Now I could just do the same thing as we did before, but instead of x, y's, and z's, I have like 4, 32, and 2 cubed. But let's do something first. Let's do the following. Notice that all of these arguments, the 4, the 32, and the 2 cubed, are all powers of 2. So I will rewrite the first one as log base 2 of 2 squared. I'll put some parentheses there just to separate it out. And then minus the log base 2 of 2 to the 5th plus the log base 2 of 2 cubed. And there are many ways to handle this problem. I'm going to handle it this way, and I might do a second way just to show you, but let's use properties of logarithms here where I can write the first one as 2 times the log base 2 of 2 minus 5 times the log base 2 of 2 plus 3 times the log base 2 of 2. Now I'm going to do an extra step here that's not really needed, but I do want to talk about it. And I will show this in a different video. But just to let you know that the log base 2 of 2 equals 1. In fact, the log base b of b equals 1. Now, why is that? It's because we could rewrite this in exponential form as 2 to the first, the base to the exponent equals the thing inside. Showing that we do have an equivalent statement. But that will be for a later video. Let's just continue with this one right here. Notice that I have 2 times the log base 2 of 2, which is 1, minus 5 times the log base 2 of 2, plus 3 times the log base 2 of 2, which equals, in total, 2 minus 5 plus 3, which is 0. So as I said, I could have handled my simplification in a different way. In fact, let's do it in a different way down here. Since I have the same base, I could have used my properties of multiplication, division, addition, subtraction to put things together. So the first term is positive, so I would have 2 squared up top. The back part is positive, so I'd have times 2 cubed up top. The middle part is negative, so we would divide by that, which gives us the log base 2 of 2 squared times 2 cubed over 2 to the 5th, which is the log base 2 of 2 to the 5th over 2 to the 5th. which is the log base 2 of 1, which we know to be 0. So there are very often multiple ways of solving problems with logarithms. In the next video, we're going to look at different types of problems with logarithms, where we still use our properties to solve things.